Hello everyone, welcome back. Today we are going to talk about force friction. And just to get things started, there are entire industries that are based on either increasing or reducing this force. To give you an idea, if you are producing, say, a sneaker for a basketball game, you're going to want as much friction between the bottom of that sneaker and the floor. In fact, this is true pretty much for any indoor sport. On the other end of the spectrum, someone who is a skier is going to want to wax their skis because that is going to produce less friction between their skis and the snow. Now, to get us started, there's a picture I would like to show you. This is a picture of a very smooth surface, believe it or not. It was done with what is called an electron microscope, which is basically a very, very powerful microscope. It's kind of difficult to see here, but the scale here says 100 micrometers, and that is 1/1,000,000th of a meter wide. The point of showing you this picture is because no matter how smooth a surface may seem to you by looking at it or touching it, on the microscopic level, it looks something like this. It is anything but smooth. But if you were to run your fingers across it, you would not notice this texture at all because the receptors in your fingers simply are not sensitive enough to do so. So what you're looking at is actually, to us, would be a very smooth surface. Now this brings us to why friction even exists in the first place. So I'm going to do basically a side view of a really smooth surface. So under an electron microscope, a side view of a very smooth surface will look something like this. It would look like a mountain range, basically. Now imagine you put something equally smooth on top of it, let's say a textbook, and again, under that magnification, it would also look a bit like a mountain range. It would not be smooth at all. Now, if I was to rest this book on top of this surface, what would happen to all these ridges and valleys? Well, they would lock into each other. This is basically what produces friction. All the ridges and valleys in the two surfaces on a microscopic level will kind of lock into each other, almost like Legos would. If you try to slide the book across a desk, there's going to be some resistance due to the fact that these ridges and valleys are locked into each other. So, to start us off, friction is a force caused by microscopic textures between two objects when they touch each other. Friction is always trying to prevent something from sliding or trying to slow an object down that is sliding. So that book on the desk, if you push it a little bit, it's not going to move because those ridges and valleys are locked into each other, and that provides a frictional force that's working against you. If you do slide the book across the desk and take your fingers off of it, the book will slow down to a stop because that frictional force will try to slow down the object until it stops. And once it stops again, those ridges and valleys will lock into each other, and the book would be more difficult to move. So let's expand this idea. And while we do that, I'm going to take this and move this picture up into the corner because I'm going to want you to keep this picture in mind. Let's say you have a couch. Here's your couch on a flat level floor. Now your couch is going to have mass, which means let's start a force diagram here. And of course, you're going to have force, earth on couch. And the couch is not going anywhere, so we're also going to have force normal on couch. Let's say the couch, we'll make it easy, let's say couch weighs 100 newtons, which means force normal is 100 newtons because there's no acceleration up or down. And we'll say you are here trying to move the couch. So you are pushing the couch to the right. I'll call this force person on couch. And there's going to be a frictional force, it's force friction, that's going to try to prevent you from moving the couch. Now, imagine if you had a younger sibling or cousin, and they walked in the room, and they sat on the couch. Would they be helping you out? They obviously would not. If they sit on the couch, that means I have an extra force downward on the couch. Now, if this force downward is added to the couch, that means the couch is being pushed more into the floor. If the couch is pushed more into the floor will push more upward, which means force normal would increase. So keep in mind, I have two forces down and one force up. Not only that, these ridges and valleys would be more locked into each other on the microscopic level. And if that's true, that would make the couch harder to push because I would have, I'm actually going to erase my person here, I would have an increase in force friction, which can make your life more difficult. Let's back up and make one slight change. Let's say someone walked in the room, instead of sitting on the couch, they immediately place their hand on the couch and push down on the couch. They are adding another force downward onto the couch. So I would have force earth on couch and force hand on couch. Let's say that's 60 newtons. What would happen to force normal? Well, I wouldn't get another force upward, but force normal would increase because the more the couch pushes on the floor, the more the floor pushes up on the couch. And this would end up being 160 newtons to match the forces downward. And if that happens, these ridges and valleys get pushed more into each other again. And again, that would increase force friction, which would make moving the couch more difficult. Let's back up and take a look at one more situation. So let's say someone walked in the room and instead of pushing down on the couch, they lifted up on the couch, but didn't lift it off the floor. They just lifted up on it a little bit. Let's say they lifted up on it, it's force hand on couch, with 20 newtons. Now, if they lift up on it with 20 newtons, then force normal can't be 100 anymore. Because if I have force earth down as 100 newtons, and I have 120 newtons upward, this couch would fly into the air. And this person obviously is not lifting up enough to lift the couch off the ground. So what happens to force normal? Well, force normal will decrease. The force the earth pulls on the couch with can't change unless the mass of the couch changes. And the mass of the couch is not changing. So when someone lifts up on the couch a little bit, they are not lifting the couch off the ground, but they're lifting it enough for these ridges and valleys to separate a little bit. And if that happens, then force friction is reduced, making your job a little easier to push the couch across the room. Now, the reason why I brought up these three situations is because I want to get a link between force friction and something that causes force friction to either increase or decrease. In the first situation, someone sat on the couch, which added a force downward and increased force normal, and force friction increased. In the second situation, someone merely pushed down on the couch, but again, that added a force downward, increased force normal, and friction increased. In this third situation, someone pushed upward, which decreased force normal, and force earth stayed the same. So which force changed with force friction each time? The one force that changed and matched what friction did each time was force normal, the force that the ground is pushing on the couch with. Keep in mind, the actual name for this is force ground perpendicular on couch. This is literally how much force the ground is pushing the couch with and how much force the couch is pushing the ground with. If this increases, these ridges and valleys get more locked into each other. If it decreases, they get more separated. And if they get pushed into each other, force friction increases, and the more they separate, the less force friction becomes. So, force friction is dependent on two variables. The first is what the two surfaces are made of. Going back to our basketball example, I want you to think about this. Imagine you and your team are about to play your rival team out on the court. Your rival team has brand new sneakers to play in, but your team has to play in wool socks. This is obviously an unfair competition, even though the only thing that really changed is the material between your feet and the floor. The other variable that force friction is dependent on is the amount of force that the two surfaces exert on each other. This is sometimes called force normal. So the idea of the two surfaces pushing into each other, we've already dealt with a few times. We've talked about force normal, how force normal can increase or decrease, and we've discussed force diagrams. However, how the materials come to play mathematically is going to be new to you, so let's talk about it. Every combination of substances have what is called a coefficient of friction. The higher the coefficient of friction, the more friction there is between the two substances. So let's take a look at my basketball example. So the coefficient of friction between rubber sneaker and the wood floor is about 0.98. Would be higher than wool socks and a wood floor, which is about 0.3. This means you would slip a lot easier if you were wearing socks, of course. So this number, the coefficient of friction, there is a coefficient of friction for every pair of substances that are known. Basically, the higher this coefficient, the more friction there will be between the two substances. So you know that rubber sneakers have more friction on a wood floor than wool socks do already, but this is the scientific backing to that observation. There is literally a number that tells you how much friction there is going to be between any two substances. So something like rubber on flat ice, however, would have a very low coefficient of friction. There's one more thing I want to state, and it's the coefficient of friction can go above 1, but it rarely does so. If you find something that does, you may want to double check it. The symbol for the coefficient of friction is called mu, and the symbol looks like an italicized script U. This was from a word processing program, obviously, but it looks something like this. This is more likely what mu looks like. It's kind of like an italic script U. Here is the expression that we are about to discuss. Force friction equals mu times force normal. That's it. But again, as most things are in physics, this is deceptively simple. You can think of mu as a percentage. So let's say the coefficient of friction is 0.8. You can literally read it like this. Force friction is 80% of force normal. So it's a pretty healthy way to think about it. It's something else you may have noticed. Mu is the first variable we have in physics that does not have a unit, because again, it's literally a percent of whatever force normal is. So let's bring back my couch because there's something else we need to discuss. There are actually two types of force friction. Let's do a thought experiment. If you're going to push a piece of heavy furniture across the room, you push on it, it starts to move. Now, once it starts to move, do you want to keep it moving across the room? Or do you want to stop after a little bit, then start it up again, let it stop, start it up again, let it stop, start it up again, let it stop? Well, if you think about it, once you get that object to start moving, you want to keep it moving. You do not want it to stop until it actually gets to its destination. And there's a reason for that. If the two surfaces are stationary relative to each other, these ridges and valleys lock in. So if this couch is not moving, these two surfaces lock in with each other, and we have what is called static friction. Static means it's not moving. Now let's say the coefficient of static friction is 0.8, and you want to move this couch. Well, I'm going to put my force friction equation over here. In this formula, there's no subscript here, but I purposely have a subscript here, and that is because I'm dealing with the friction when this couch is stationary. I do my equation, force friction static equals 0.8 or 80% times force normal, which is 100 newtons, and I get 80 newtons. Now, let's say you push on this couch, I'll say force person on couch, with 30 newtons of force. My question is, what is force friction right now? Force friction cannot be 80 newtons. If you walked up to an object and pushed on it, and force friction is greater than your push, that means you would basically walk to a couch, push on it, and it would tackle you. So what does the 80 newtons actually mean? The 80 newtons is the limit that this static frictional force can use to prevent you from moving the couch. That's what it wants. It does not want you to move the couch. That's its goal. So it will only use as much force as it needs to prevent you from moving the couch. If you push with 30, it will push with 30 newtons, and the couch will not move. If you push with 50 newtons, it will push with 50 newtons, and the couch will not move. If you push with 79 newtons, it will push with 79 newtons, and the couch will not move. However, if you push with 80 newtons, and technically a hair more, this couch will move. Now, I want to take a moment and specify something about what I just said. Any force larger than the static force of friction will make this couch move, which means if you pushed with 80.000000001, this couch will move. Now, that is well within our rounding errors for physics. So, to keep it simple, here is the common assumption used in any first-year physics course and for the AP exam. Once you match force friction static is broken, which means as soon as you hit this value, the couch will move. And once that couch moves, this is no longer a static situation, and force friction static is gone. Before we talk about what happens next, let's actually get force friction static in our notes. So there are two types. First type, static friction, uses mu static. The amount of static friction represents a limit of how much force it can use in order to prevent an object from sliding. So this word, which I've underlined now twice, is extremely important. Force friction static is a limit force. In the example we just did, force friction static was 80 newtons. You push with 10, it pushes with 10. You push with 30, it pushes with 30. You push with 70, it pushes with 70. However, once you hit 80, force friction static is broken. Now, when force friction static is broken, what happens? Let's discuss that. So here's our situation again. You push 80 newtons. You have now broken force friction static. What happens? Well, there is a second coefficient of friction. The second coefficient of friction is called mu kinetic for motion. Let's say this is 0.3. Now, one thing I'll mention right now is the coefficient of kinetic friction is always going to be lower than the coefficient of static friction, because once these ridges and valleys start sliding over each other, they don't have time to lock into place again. So there's still friction because they're rubbing over each other, but not as much as if they were locked. So once this couch starts moving, what happens to force friction? Let's find out. Notice the formula itself is going to remain the same. However, I'm now using force friction kinetic instead of static, which means I'm using 0.3 or 30% of force normal, which is 100 newtons, which means force friction kinetic is 30 newtons. Now, as soon as force friction static is broken, force friction drops immediately to force friction kinetic value. So it would drop immediately from 80 newtons down to 30 newtons. Now, the interesting thing about force friction kinetic is it's the easy one. Once you find this value, unless force normal changes, this value will not change. So you pushing on the couch horizontally, it no longer matters how much force you push on the couch with. The only things that do matter is if force normal doesn't change and if the couch is actually still moving. So in this situation, if you keep pushing with 80 newtons, you now have an unbalanced force and this couch will speed up. Let's say you pushed with 10 newtons. Well, if you push with 10 newtons, then we have a 20 newton imbalance to the left, which means the couch would slow down. And here's a very important and familiar question. What would happen if you pushed with 30 newtons? Well, once you break static friction, the couch is now moving. If you reduce your force to 30 newtons and match force friction kinetic, that means there's no net force. No net force means there is no acceleration. And if there is no acceleration, the couch will remain at a constant velocity. So let's get some notes down on our second version of friction. The second type of friction is kinetic friction. Uses mu kinetic. Kinetic friction is a constant amount of force that tries to slow an object down. As long as the object is moving, force friction kinetic will not change. And I'll put one caveat on that. Force normal can't change either. Because as you saw with the equation, if force normal was to change for some reason, then force friction would change as well. But that's actually pretty rare in a problem. So again, force friction static is a limit force. If you're pushing that couch, if you push with anything lower than that limit, the couch will not move. Once you hit that limit, force friction static is broken and the couch moves. If the couch is moving, force friction kinetic comes into play, and force friction kinetic does not change. If you push more than that force, the couch will speed up. If you push less than that force, the couch will slow down. If you take your hands off the couch, it will slow down. If you push with the exact same amount of force as force friction kinetic, then the couch will move at a constant velocity. Here are some actual coefficients of friction. And if you'll notice, the static variables are always larger than the kinetic variables. So to finish up here, let me show you one more thing. So I wanted to show you a visual version of what we were just discussing. I have a little man here, and he's going to push this filing cabinet. His force is going to be in blue, and the frictional force is going to be in red. Now, if you notice, he's pushing on it. The filing cabinet's going nowhere, because right now he's dealing with static friction. He pushes, and static friction will match him exactly to prevent the filing cabinet from moving. Now, as I increase, watch what happens carefully. Up, 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 up. You catch it? Force friction changed instantly. I'm gonna let go. Friction slows it down. Watch me do it one more time. So force and static increase, 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 increase. Now you can watch the instant it switches to kinetic. Right there. And I could do more, it speeds up. I could do less, it slows down. And notice force friction is always against the direction of motion, not the direction of my force. So watch this. Blue is to the left and red is to the right. But watch what happens when I do this. I'm going to push the other way. And notice they're in the same direction now. Let me do one more time. Push here, force friction wants to slow it down. So here, force friction and the guy both try to slow it down. So force friction opposes motion. It does not oppose your force. That's something else important to keep in mind. All right, I think this video is long enough for everyone. Have a good day. This is Mr. M signing off.